I'm reminded of a book that was written in 1967 by Dr. Harris, and I was pretty young at that time, but I read it when I was in university, and the book is called I Am Okay, You're Okay. And this book, even now, it is still being sold, and over 15 million copies have been sold. And it is still considered to be a fundamental writing on human psychology. And Dr. Harris actually proposed at that time that the whole human psychology and relationships are built around three players or three roles that we play as human beings: the parent, adult, and child. And then he built up a whole system around this one for the transaction analysis between humans. So he defined what the role of the parent is, adult is, and child is, and how these relationships define everything that we do. And after that, as you can imagine, many people wrote more books. Somebody said, I'm okay, you're not okay, you're not okay, I'm okay, that kind of thing. So it was a very popular topic for many years to come. And I was thinking that maybe the same thing could be true for structures. And we may identify four players or four roles on which the entire structural mechanics is built, just like the human psychology is built on these three roles. So those are stress, strain, force, and deformation, and their derivatives we will see. So now we are going to look at how these four players and their relationships almost entirely define the structural mechanics and various games that the structure played, as we will see. So there's a relationship between stress and strain, another one between force and stress, another one between strain and deformation to force. And there could also be indirect relationship between strain and force and stress and deformation, which we will also explore. So this is the framework that we are going to start with. And if you look at the relationships in human beings, you can have relationship with instantaneous, short-term, long-term, stable, broken, bonded, invalid, rigid, absent. All of these define various states of human relationship. And I can assure you that the structural relationships also are valid. Any word that you pick also defines a relationship between these four players and define a structural response. So, which means that the humans and structures are not very different, and that's how we are starting this conversation. Now, let's move forward. First of all, stress and strain, normally they're related by what we call constitutive law, the relationship between stress and strain. And then the force and stress are related to what is called the stress resultant concept. The strain and deformation are related through compatibility, that nothing is broken, thing is continuous. And then the force and displacement or deformation. So we will use deformation and displacement interchangeably. They both mean the same in this context, although they have clear difference in detail, but I'm using them in the same context. So we have equilibrium equation. So these are the kind of four basic relationships that we can start with. And these relationships, if they are fully linear and they are elastic, then we can start from any one direction, from any one given quantity, and go through this and come back to the same quantity. So that means each relationship is interconnected, and they are also linear in the sense that you start with a number, you follow, go back, and it also doesn't matter which direction you go. You can solve this relationship cycle from both directions, and you can complete the cycle, and you can keep on going. However, these relationships are not always linear. There is a nonlinearity between them. So constitutive law, all of these relationships that we talked about have a nonlinearity component there, which will come from geometry and materials, displacements, buckling, P delta, many things that make these individual one nonlinear and nonlinear. And in that case, then they are, first of all, the cycle is broken. You can't always complete the flow, especially when the material is like reinforced concrete, which is not homogeneous and also has composite properties. and different materials make one cross-section and so on, this may not work. And also the direction is also important. So these are the starting sort of principles on which we are building it. Now, the relationships can also be dynamic. So each of these relationships that I mentioned again, previously, they can all have a dynamic component, and mass, damping, natural frequencies, ground motion, many things will come because of that and from there. So we have nonlinearity, we have dynamics, we have linearity. All of the relationships could be affected by them. Dynamics can also occur in the other two sides, but it's not so significant. Okay, so we have the basic definitions now. Now what I'm going to do is to move from each relationship, and then finally we will see how we can create structural games out of these, starting with the basic one, stress and strain, the constitutive laws. And if you remember, this started long time ago. But before we go there, there's few questions I would like to ask you, or I would like you to think about. Does stress produce strain, or does strain cause stress? And can strain exist without stress? And can stress and strain have no relationship whatsoever? Can they exist independent for each other? And there are cases that can happen. For example, creep is one, the relaxation is another one, temperature variation is another one. So sometimes they are not really independent, they're not really connected, and they can exist independently. So they may cause each other, they may not cause each other, or they may exist independently of each other. So that is something about the strains. Then, and stresses. So if you go to the origins of this one, I think we can trace it back to these two guys, Robert Hooke, who proposed the basic, the concept that the two are force and displacement or deformation are related, and then Thomas Young, which explicitly found the relationship between stress and strain long time ago, over a period of almost 200 years, and it's been a long time since this was determined. So that's where it all started. Now, if you look at a small piece of a material, and then you can see that if you use three-dimensional system, you have three stresses on each and three strains on each face, and then because of the directionality, until we end up with 6 unique numbers, and based on that, the relationship can be defined through this matrix. So this is the minimal linear elastic model relationship of a material, including the Poisson's ratio, which links them together. So you can see we have 6 independent stresses, 6 independent strains connected through this matrix. So it's not a very single E as we saw earlier. But in reality, that matrix is only giving you the numbers at one point on the stress-strain sort of relationship. It's not applicable throughout the history. As you can see from here, if there's a strain and a stress, it will vary in a number of ways and in a complex manner, and it can be linear, then it can yield, it can have hardening and fracture. So from that, you can derive actually several specialized relations, for example, brittle and ductile, and all kinds of relationships: linear, elastic, linear inelastic, nonlinear elastic, nonlinear inelastic. So we can create several specific models from this basic concept of the stress-strain relationship, which we now know is not linear and it's not the same at each point along the strain. And this is the starting point of the difficulties that we as structural engineers face. On top of that, we also have this problem of the number of directions. These stress and strains are dependent or independent. Isotropic, for example, is a simple one, same behavior in all directions. Uncoupled, orthotropic is different behavior in orthogonal direction, behavior is still uncoupled. And anisotropic, when different behavior in 3 directions and behavior is also coupled. And this creates further complexity, but because the stress-strain curve that you saw was only in one direction. So if they are interdependent, they are coupled, then the whole system becomes highly complex. And that's why in finite element analysis and modeling, material models are still one of the most difficult things to handle. And many software keep trying. We just don't have enough material models to represent the real behavior that we observe in reality. So stress-strain relationship gets also affected by composition of material, the confinement effects, the initial condition, state of strain, rate of strain, direction of strain, history of strain, time since the initial strain, and so on, and also temperature. So not only that they are interdependent, they're also dependent on many other factors, even age. So which means that for concrete and other materials. So that means the material definition, material relationship is probably one of the most complex one to resolve through all stages and all types of materials. And then we have dynamic effects on the material. We have strain rate effects, inertial effects, damping effects, nonlinear material behavior and cyclic loading, and dynamic modulus of plasticity. So there are further complications or further effects on this relationship coming from not only nonlinearity and dependence on each other and direction, but also from dynamics. And that's one of the reasons that it's so difficult to model the materials accurately. And programs like ANSYS and those sophisticated programs, they create many material models to handle these special cases. So you can actually create a mind map of the whole material behavior, directionality, stress strain, and keep on going, and this can actually keep expanding. So this is just a starting map of a material constitutive law. And as you can see, you can appreciate how complex this is getting to be. Okay, so moving on, I'm sure if you have studied in the universities and you have seen this test, and now you can see that if you are loading a cylinder, it actually breaks not by compression, but by bursting out on the direction normal to the direction of loading. And that is because of the Poisson's effect, which, like you saw in the original equation, affects the strain in one direction, causing strain in the other direction. So that's another important observation, which actually brings us to the confinement of RC sections, where we can use this effect to our advantage by not allowing it to have the strain in perpendicular direction or limiting the strain, hence increasing the capacity or behavior along the primary direction of loading. So that way, the Poisson's effects can be manipulated in a way to provide better axial response in the primary direction. And that's something that we will come back in a few minutes again. So confinement, as you can see now, is one of talking about reinforced concrete, and especially going to the nonlinear analysis and earthquakes analysis, this is one of the most important things that we have got to consider if we are going to accurately model the concrete structures or determine their response in close to reality. So confinement, as you can see in a column here, is heavily confined, the other one is not confined. And then you can get different material relationship, one for the outer cover and one for the core, which is confined, very different from each other. In fact, they're not on the same scale. If you put on the same scale, the unconfined is extremely small capacity of strain, 0.0035 or 0.004 or maybe 0.005 at most, and confined can go as high as a 0.03 or 0.05 even. So you can see that we can drastically improve or alter the stress-strain relationship of concrete through confinement. So let's move on to the next one. We'll come back to these again. Stress, force and stress. This is a simple one, relatively simple one, because in typical analysis, we can calculate so if we go back to that strain, stress components, we can actually calculate the stress within the linear elastic range for homogeneous materials, homogeneous sections, by simply dividing the force by the corresponding property of the cross-section. For example, P divided by A gives you axial stress, moment divided by section modulus gives you axial stress due to moment, and so on. So you can calculate the elastic stresses through simple formulas linking the geometry of the cross-section with the force leading to the stress. So because these are But the problem here is that this equation, when you combine the stresses from different actions, because like I mentioned, axial stress is produced by axial load, but also produced by bending moments and also produced by torsion. So if you calculate the axial stress, then you can see that you can elastically, in elastic range, you can add them together. But this is only true when the cross-section is homogeneous and linear elastic. When the cross-sections are composite, made of many materials, then we can, but still linear and elastic, we can still do the equation, but now we have to introduce the concept of the modular ratio linking their stiffness. The previous one, stiffness is not there anywhere. It's independent of stiffness. But in the second one now, because of the two materials, the stress produced will be relative to the stiffness. So that's the modification that needs to be made. And if you look at the programs like CSS Section Builder or other programs like that, you can actually see the combined stress plots from bending moments and so on. And you can also calculate them on composite sections. So this is all possible because we are using the combined stress approach modified by modular ratio. Okay, now let's look at this poor beam. The poor beam, I'm calling it a poor beam because it has shear, moment, torsion, and axial load all applied to it. And if that is the case, then the stress state will be now a combination of the stresses produced by all of them, as I mentioned earlier. So we could have a beam now along the length in which we could have these cases. We could have axial tension, we could have axial compression, we could have the shear, pure shear, we could have pure shear plus tension plus compression, we could have moment, axial stress due to moment, and we could also have the shear stress due to torsion. So you can see here, any element, we can have axial stresses coming from several actions, shear stresses also coming from several actions. So there's a multitude of things happening on every location of the beam, the stress state will be unique, even for a simple beam subjected to uniform load. So, and then the Mohr circle will come in and those kind of things. So that's the point, that the stress and force relationship, even though they are simple, but because of these complications that one stress is produced by many actions, we can end up this equation and cannot go back. You cannot take the axial stress and determine bending moment and the axial force components directly because you don't know which one caused what part in a real structure. Okay, so let's go back again to our history, and look at these guys who did some work. So those two on the left proposed the beam theory hypothesis of Bernoulli's or plane sections remain plane after bending, which gave us the ability to have that superposition principle and also the ability to back compute the things from the stress. And they said this is great, people use that. But then the other guy, Saint Venant, came in and he said, no, wait a minute, this is not really true. It is only true after the distance from the load application and not close to the load application. So he gave those nonlinear distribution of the stress because of the localized effects. And that made the determination of stresses very complicated now because we don't know what the nonlinearity of the stress distribution is. So we can't use the area things anymore that we just used. So that's the problem coming from nonlinear. And this goes on, wind load, you have the building, whole, especially tubular structures and all, you have the shear lag problem. And shear lag problem exists in T-beams, exists in steel sections, exists in buildings, and everywhere. You see this shear lag problem, which is basically nonlinear distribution of the stresses as we go far from the stiff parts of the structure and so on. So that we can see that, okay, now we can't really use the basic equations anymore. And then we have another problem here. We have interaction. We have load and moment interaction, moment and moment interaction, shear and torsion interaction, shear and moment interaction, torsion and moment, and shear, torsion, moment interaction. And on a three-dimensional or a 3D frame, which with the 6 degrees of freedom and 6 actions, in fact 7, including torsion and warping, you can see that now these interactions will further complicate the determination of the stresses forward and backwards. So it's no longer easy because of these interactions, and especially if the cross-section is not homogeneous. It makes it further difficult. So for the design action sets, we will come back to this slide again. We have two moments and one shear, and we have axial load and so on. So we can see clearly that we cannot now design things only for one action because of these interactions that exist. And like I said, we'll come back and visit this in a few minutes again. So now we have two problems here. One is the stress coming from the force, which is calculated by section properties. And the second one is the capacity coming from a certain failure criteria. And now we have a stress interaction, and we have a capacity interaction, and demand interaction, and so on. So we have several interactions going on at this point. The interaction between different actions, moment and axial load. For example, stress coming from moment and axial load, and so on, and the capacity also being affected. And these are all kind of independent. So let's go and look at them. So like I said, basic interaction of the stresses is the first equation. And the second one is the interaction of the DC ratios, which is now comparing the demand versus capacity and saying, okay, this combined DC ratio should be less than 1. So this is very good and true for, once again, steel maybe. For reinforced concrete, it may not work as simply as it is shown here, because we don't have the same material everywhere. So we can see that we have the equations, but their application is limited to a certain type of structure, certain range of behavior. Now we look at the load and moment interaction capacity-wise. So the capacity of a cross-section for a certain failure criteria will have an interaction like this one. There's a 3D interaction between 3, and then there are 2D interaction between the two, moment and load, and 2 moments in this direction. So this is the first load moment and moment interaction of the capacities based on a failure criteria. This is torsion and shear interaction based on the capacity versus demand once again. And this is the shear and moment interaction once again with capacity and demand. And this one is a torsion moment interaction. And then, so you can see here that we have capacity interactions which reduce one capacity in the presence of the other load. And this, as you can see clearly, is no longer a simple case of stress to force or force to stress anymore, because now all of these interactions need to be considered before we can relate them together. And moving on to strain and deformation. This is actually, at this point, I'm keeping it very simple. And we just think this is compatibility. That means we have strain and displacement. Basically, you just can calculate the strain by dividing the deformation or displacement by the length of the structure in this case, or the curvature, and so on. So we can link them together by simple geometry and compatibility of the deformations. Here, so you can see from here that the axial load can be then calculated or can be assumed. But we can determine the strain only from deformation. Load is not necessary. As long as deformation is present, strain can be calculated. And similarly, if the strain is present, we can calculate the corresponding deformation. Load does not come into play for that. But later we will see that when we really apply it, it's not really independent. So we have axial deformation, rotation, curvature, axial strain. So basically we have shear strains and axial strains primarily coming from various deformation types. And they all interact and combine with each other, just like the forces and demands. And the fourth one, a big one, is now the force and deformation equilibrium relationship. And this is where I think we see a lot of difficulties. We already see stress-strain relationship as one of them. Also, force stress is not simple, but force deformation is another one where we will see many variations. Okay, so at the very basic, this was proposed by Robert Hooke. As I mentioned, he said that the force and displacement are proportional. He didn't know exactly what is the proportionality constant until we know later that it is the stiffness over there. So we have this relationship between the two. And this is actually true for materials and structures and everything. And you can see here that the deflection is calculated, can be easily for elastic system, deflection can be calculated by using these simple equations from strength of materials that we had studied a long time ago. They're all forms of force deformation relationships. They are clearly related to each other by stiffness properties. But the problem is that the stiffness that Robert Hooke or other people use in this case is basically assumed to be linear. But the observation, so we have this, any point on the curve is the same, giving you the same stiffness. But observations tell us that that's not the case. The actual structure, especially reinforced concrete, becomes nonlinear quite early due to cracking, due to many, many reasons. So that means the blue line is the real behavior, which means that the linear application of the equation is not valid. So if that is the case, we need to find the nonlinear force corresponding to a displacement and that relationship and the corresponding stiffness and the difference between the linear and the nonlinear force can tell us something about the change in stiffness. So from that, you can then go back and modify your linear equation to include the nonlinearity. That correction of force will come here, and now our system becomes nonlinear as long as we can calculate that corrective force for nonlinearity. Now, this nonlinearity, the problem is it exists everywhere. It exists at the material because the stress strain curves, as I showed you, are highly nonlinear. So the constitutive law is nonlinear by definition, or especially concrete. Then we have because of that, and because of section cracking and section changes, we have the nonlinear moment curvature, for example. So next stage is that the moment and curvature, load deformation becomes nonlinear. And the moment rotation becomes nonlinear. And the whole structure becomes nonlinear, force displacement becomes nonlinear. So we built up the nonlinearity. For structural geometry, you also have the P delta effects, you have large displacement effect, you have other things going on, the construction sequence effects, many effects that make it nonlinear. So there's a whole accumulation of nonlinearity over the structure by the time it deforms, especially during an earthquake. So that's the situation regarding nonlinearity. Let's move on. So this goes from this to this. Okay, it adds up. Now, let's go back to dynamics now. So far, we have not talked about dynamics in other properties because they were not significant. But for force displacement, dynamics is very important, more critical than the others. And there are two competing equations coming from Hooke and Newton. Newton is talking about a body which cannot be deformed, just moving. And Robert Hooke is talking about a body which is fixed, can only move a little bit, and it's at stage, it's not moving. It's after the force deformation, it becomes stable. It's an equilibrium. Both are different equilibriums. But if we combine them together, we get the linear dynamic relationship. So you can see here, if you combine the equation from Hooke and Newton into one system, and then later we also add the damping there because of the material is real, and then we add the ground motion, you get the full picture of the dynamic system, linear dynamic system for any given force, and then for ground motion, force generated due to ground acceleration. Ground acceleration and the applied force changing with time, both can be handled by this linear dynamic relationship. So that's the evolution of the equilibrium equation into dynamics. Then we bring back nonlinearity, as you remember here, and add it back to this system and to this one, and we have the full picture. Now we have an equilibrium system which accounts for Hooke's stiffness-based displacement relationship, Newton's mass acceleration-based system, and damping of the material in several kinds of damping. And then from there, we can have the ground motion equation. So this is a complete picture, almost complete picture of the nonlinear dynamic force displacement relationship. Please remember, acceleration is a derivative of displacement and velocity is a derivative of displacement. So there's still a displacement-based equation. The primary variable still being displacement. So these relationships can be too flexible. They could lack unstable because of too flexible, lack of restraint, no equilibrium, buckling, P delta, capital P delta, small p delta, it should be small p delta over there, and large displacement. So this can further be affected by those which are not explicitly shown here, but they are all part of nonlinearity. Okay, so now we have the 4 relationships defined both for linear, nonlinear, static, and dynamic cases. Let's see what are the game plans that we can solve or we can play by using these 4 players, and what is our target in each game? What do we want to win? What are we doing? Let's look into that. Let's start. Remember, we have these 4 players. I keep reminding you that. And then we have 2 basic game plans. The left side game plan says that we have applied loads, and I want to calculate from structural analysis using the equilibrium equations. We will calculate the force, the displacements, and from there back compute the forces. Once we go from force to displacement and then displacement back to force. And then from there, we can calculate the stresses, and we'll say, okay, I will check on the stresses because this is a valid path only when everything is linear. Second is, it says, no, I don't want to go that way. I actually want to start with the material response because failure is controlled by material failure. So, and it's not controlled by stress failure, but rather strain failure, because things break or fail because strain is large, not because stress is large. Breaking or disintegration is because of the strain and displacement, not because of the stress or force. So if you if you put the limits on the strains on the behavior, even stress, doesn't matter, and you start from there and determine the cross-section response, then member response, then structural response, using what I showed you earlier, built up from step by step, the stiffness, and then you calculate the load capacity, then you can check the DC ratio. So these are 2 separate ways to play the game. Left side normally called working stress approach, and right side called ultimate strength approach in traditional design. Of course, we will go beyond that. So these are the 2 basic game plans. So let's now let's see how we can play them. Game number 1, designing an RC building. So the objective is, this is the most common game that we all structural engineers play. I want to design a building. Make sure the capacity is more than demand. DC ratio is more than 1. That's all we are looking for in our design, our calculations. Game plan is analyze the building, determine the demands using design code procedures. Play number 2 is compute the capacity using design code procedures. Play number 3 is compare demand and capacity, and we are done. So this is the game, and that's the game plan. So let's see how this correlates with the 4 players. What are they doing in this game? How are they playing? What is their role? So typically, from loads to actions, we will do the analysis. From actions, we can calculate the deformation, but we will not go that way. We can calculate, but we will know that they are not reliable. We will not do that. We can assume the deformations, strains on one side, go back to stresses, go back to stress resultant, compare them with the actions that we determine, and check the DC ratio. That's how the strength design will work. And this will happen in many steps. You start with the loads, you create load case practically. You will have the loads, create load cases, load combinations, design envelopes, design actions, and design action sets. Remember, these actions are not independent. They are coupled. They have interaction with each other. So we cannot take one at a time. You cannot design only for moment. You have to design for moment and axial force together, and moment and shear together, and shear and torsion together. So those interactions have to be part of this system. Now, seismic demand is calculated by this approach, which I showed in a couple of previous webinars. Basically, the code, especially the ACI and ASC codes, say that you can take the actual estimated elastic demand divided by R, increased by omega, then you get that estimated nonlinear curve. But you fix a design level there, you don't care about the green or the gray area. You calculate a design level, and for that design level, you check the capacity and DC ratios. And that's simplified, extremely simplified, because of those factors. So even though we have developed the full nonlinear dynamic ground motion equation in our previous slides, we are not using it completely for the code because we can't. So we use a subpart of that. We use the modal part to calculate the modal response, and we use the equivalent static part to convert the force, seismic force, into an equivalent force and apply it and do the analysis. And then we do the response spectrum analysis. Also, if we are if we are doing a good job, we do the response spectrum also. And for wind load and other loads, we use a simple equation of the equilibrium. So basically, from that equation, we only use some parts of the equation or linear, mostly non-dynamic, except the modal response. And then we calculate that response and use the code factors to determine the demand. Then, on the capacity side, this is the real cross-section. On the capacity side, we are doing a slightly better job because we take, but not a great, I will tell you what's the difference. So we start with the cross-section, and from there, we can actually determine the stress resultants based on the stresses. And here, we use the deformation to strain relationship, plane section remain plane for rotation to calculate strain profile. From strain to stress, we use the constitutive law to get the stresses because we have got the strains now, assumed strains, and we fix the strain to be a failure criteria 0.003, 0.0035, and we say, okay, we cannot have deformation more than that. Then we use the stress to force relationship and get those force components. So we have now determined the section capacity, including this relationship, but we are still not exploiting everything because still we're using the code-specified formulas to do that. So based on that, actually we can then determine this interaction surface. I'm sure everybody has seen that. So it's a capacity interaction surface between two moments and one axial load, and then this capacity interaction surface can yield a PM curve and an MM interaction curve, as we talked about before, those two interactions. So the three interactions are split into two separate two interactions, and then we use them to compute all the capacities for design purposes. So all of the design is based on either the first or the second. Okay, so now we have it, the capacity interaction. Now let's go back to a real building and see how everything is working, put everything together. And we are going to give an example of ETABS, of course. So let's have we have a building, and then from that we have the structure. We take the non-structural parts out, plants and whatever. This is a big step, how many things you keep, how many you take out. But anyway, you take out things, then you create a model in ETABS, use whatever assumptions you make. From there, the model will be analyzed using the equation that I showed you earlier. The equilibrium equation, ETABS will use those equilibrium equations in a matrix form using finite element, solve those equations and give you the forces in the members. And then from the cross-section side, the program will calculate the capacity based on the code equations, and then we have the capacity, we have the demand, and it will compare the DC ratio, and then it will plot the DC ratio on each column, each beam, and you will say, I'm done. So that's the game is complete. You have achieved your objective, and now you can see here how all of those four played their part, not completely because we didn't let them go dynamic, we didn't let them go nonlinear. We put everything in the linear range. So that's game number one. Game two, the big one. You want to do the performance-based design of an RC building, not the code-based design anymore. In this game, objective is to make sure the performance is acceptable. And now game plan is different. Play number one is create a model of the building as designed, not as assumed, prepare for nonlinear analysis, because it's going to be not linear analysis anymore, carry out nonlinear and dynamic analysis if possible, and check the performance points. So now the plan is different, and now all of the players have to really bring in their best for this to work. You cannot hold back anything if you want to play this game. So going back to the preparation of the nonlinear model, you will need to consider the material nonlinearity all the way. You will need to consider the confinements and everything. You will need to generate the section nonlinearity here, cracking and all. You will need to convert that into moment rotation curves or whatever, put them into the model, and then do the analysis. So that's the preparing for the nonlinear modeling. It should be nonlinear, not nonlinear. Small mistake here. Anyway, so to go there, let me step back and see how do we prepare the model for nonlinear analysis and what is the big deal about that. So I will revisit now the two relationships, force to stress and stress to strain, because now they are not going to be as simple as previous ones. And the reason is very simple. Now let me start with case number one. Case number one is that I'm just saying that force to stress to strain. So I will just apply that force, and that force causes a certain stress. Directly we can calculate stress P divided by A, and then I plot it on the stress strain curve. And you can immediately see the problem. I'm getting two strain values for the same stress, which is obviously now a problem because I don't know which one is correct, which one I should use. You might argue that I should use the smaller one, but that's not really true because I don't know the real strain is going to be. Earthquake will definitely exceed the E1, the S1, the E1. So which means that I can't use this approach to determine strain from stresses anymore. So that's the problem here. So instead, and the stress could be outside the whole range, you don't know. So that means it has no solution. So either it has multiple solutions or it has no solution. Both cases, it's not a good thing. So that means this is not a good way to go. So the working stress method that we thought earlier won't work. Then we go the other way. I was like, fine, I will not do that. Let me start with an assumed deformation and an assumed strain, and let me fix that strain to a certain value, and then from that strain, I can go back to the stress strain curve and I can calculate the corresponding stress, and then I can calculate another stress from another strain, and I can calculate all possible stresses at all possible strains because I have unique number in every case. And then I can multiply that stress by the area and I can get the P, which means I can get the capacity of the section now, which means that now I know how much load this section can carry for a certain strain limit. And if I limit the strain to be 0.0035, then I know what is the maximum capacity. So I have the capacity with me now, explicitly, which is related to strain, and it will change depending upon the stress strain curve and also change on the strain value that is assumed. That's what the codes are doing for calculating the moment capacity or axial capacity by giving the strain value 0.0035 or 0.023, depending upon which code you're using. So that's the good thing. So that means strain to force capacity is a valid path to take for this work. But we need to do a little bit more work now. So if you have this idea that you have a deformation, you have strain, and then you have this stress, limiting strain, then you can go to the stress strain curves of multiple materials. Previous one was one material, go to multiple materials, calculate their corresponding stresses, and then calculate the total force. That means now we can handle composite sections easily because now each material follows its own stress strain curve and gets its own contribution for the same compatible strain. And that's great because now we have a nice way to compute the capacity of composites and reinforced sections including nonlinearity in its scope. So that's what we get perfectly. And this is great. So we are now using the stress-strain relationship, strain-deformation relationship, and stress-force relationship, all two of them, and link everything together. So now stress-strain applied to a section can give us a load deformation. And that's the beauty of this thing. Because now you have a way to determine the valid nonlinear force deformation relationship from this direction, which earlier was not possible. And you can determine the stiffness. That means now you know the nonlinear stiffness to be used for analysis, not the assumed E or K that you thought earlier was there. So, and this is based on deformation. So this is the key where we are preparing the model for nonlinear analysis by determining the nonlinear load deformation relationship, which will replace the assumed linear relationship coming from stiffness matrices or finite element formulations. And we can now include the confinement models there. We can do anything because we have nonlinear capability. So you can consider these all columns in your model, and you can get different concrete models for each one of them. You can see the difference. Unconfined and heavily confined models gives drastically different stress-strain curves, and they'll be critical in determining the real nonlinear behavior, because now you can find the difference between a structural response of a column with no confinement to a structural response of a column with lots of confinement, which is the design code procedures do not give, because PM diagram is not affected by confinement. So now you have clearly brought a lot of richness to your models. And now you can see the axial strain versus axial load will be so different depending upon what kind of columns are we using. And this is exactly what we need for seismic demand, because seismic demand will exceed the assumed linear range. So we can go one more step. We can put axial load, and then we can find combined curvature and axial force together. So we put curvature plus axial together. We do that. We do same procedure. We follow exactly the same procedure, nothing different. And then we use this equation to calculate both P and moment. And for each variation of strain and neutral axis, we get a different moment. And you can use this to plot the moment curvature curve like this one here. And that gives us the ability to link the curvature versus moment, which is very critical because we can bring it back to stiffness once again. And this can give you the valid nonlinear force deformation relationship for moment and curvature, which is critical, and give you the stiffness. Not only that, it will also give you the corresponding stress strain and every information. So that's great. We have talked about moment curvature in other webinars also. So there we are. So now we are ready. So we bring all that work back to the frame, simple frame. We bring concrete steel to cross-section, moment curvature to a moment rotation applied to a hinge, and then we applied the forces or the displacement to the structure, and we get the pushover curve, which is now the response of the structure. Nonlinear response of the structure, displacement versus shear force, base shear. So you can see from here, stress to strain nonlinear, curvature to moment nonlinear, rotation to moment nonlinear, finally base shear to displacement nonlinear. We got everything in the model now. So if you model this way and do the analysis, you can consider all of this into your system. And now we are ready for evaluation of a structure, which includes confinement, which includes actual reinforcement, which includes everything, reality, as close to reality as we can go. But we are still missing a few things here: bond, slippage, splice, bar buckling, shear flexure interaction. There are still weaknesses here, but we are quite close to our theoretical system. And you can't really say this is absolutely true, because like I said, we are still missing a few things. But more importantly, we are missing this one. We are missing the cyclic degradation of the materials. That means we are only considering so far one directional loading. But when we load and unload, we have degradation, we have energy dissipation, And we need to consider the hysteresis of the material also on top of the nonlinear in one direction. So this is one more thing that we need to add. So we have different types of hysteresis. So this hysteresis model needs to be added to the nonlinear model to complete the story. And then from there, you can go the realistic site-specific hazard analysis, nonlinear pushover analysis, nonlinear time history analysis, KPIs, and realistic performance evaluation. So that means now we have done it all. So going back, we have used the full equation now. We have used the entire nonlinear dynamics equation for our purpose, and we have used everything in between. So if we apply to a simple structure, this is a small frame that we test. You apply the lateral load, and you get a displacement and a base reaction. You plot it, and then you will get this plot. So if you use the linear approach, you get the light blue line. If you use the cracked assumption based on the code, you get another reduced stiffness, but still linear line. You don't get nonlinearity. But if you include the nonlinearity into this one, nonlinear plastic hinges with P delta, you can see that the curve starts to keep dropping, and you get much less capacity for force for a same displacement. And you can see here, for example, for this one, 0.5% drift, you get 20 millimeter force factor, let's say 1. This one, 2% drift, force factor 3. 4% drift, force factor 8. That means the force is reduced by 8 times by using nonlinear analysis compared to a linear analysis using the code cracked section analysis. That's it. Well, just one case. Of course, it can vary. I'm just giving you a simple sample case, but just an idea that nonlinear analysis reduces the force capacity so much. So this is quite in line with what I showed you earlier from the ACI and ASC codes. They also do this reduction, the R reduction. So you can see that R reduction coming from the linear lines to nonlinear line. And that is based on similar studies and research and analysis. They have determined these R factors and omega factors. Now, how about energy? One more thing. Energy is everywhere. So we have the strain energy, which is the area under the stress strain curve, like this one. And we have then, if it is nonlinear, then we have this one. So I don't want to go into too much detail. We'll discuss it some other time. But you get the strain energy from the stress strain curve. You get the energy per unit length, flexural energy from the moment curvature curve or force deformation moment and curvature curve, same way. So you get these energies also calculated from the basic two quantities, relationships that we have, force deformation relationship, work basically. And then you can build up the energy same way, material energy, cross-section energy, member energy, structural energy, same way. And then you can see that you can build the response up like that one, strong material. So now we have all the components with us to do this entire thing, starting with very basic 4 things. So we are almost close to the end now. So now we can progress from the code-based design to performance-based design and intuitive design, and we can go further by using the same line of discussion. So we have now come directly to determine the nonlinear response. We don't need any R factor. We don't need any other response reduction factors. We got this curve directly, and we can correlate it with the seismic demand and check against the performance, service level, intermediate level, collapse level, and everything. So that's the game is complete. We have kind of won the PBD game as well. So now you can see that we have played 2 games with these players with different results. In one, we simply verified the DC ratio. In the second game, we actually determined the real performance indicators. Okay, so that's the ending. Just want you to remember that these are the 4 players, and they have taken us from linear elastic to nonlinear dynamic analysis, and they have also taken us from code-based design to performance design. And with that, thank you so much, everyone.